So imagine you're an engineer, right?
Yeah.
You are writing a deployment script for this massive machine learning pipeline, and you're moving fast. So naturally, you use an AI coding assistant.
Yeah, like everyone does now.
Exactly.
Yeah.
And the AI says, hey, you should import this library called Secure ML Tensor Utils. It's going to handle your matrix multiplication perfectly.
Yeah, and super helpful.
Right. So you drop it in, the syntax highlighting looks great, no red squiggles, and you push it straight to production. But here's the kicker. That package, Secure ML Tensor Utils, it doesn't actually exist.
Right, the AI just completely hallucinated the whole thing.
Yes, it totally made it up. But an attacker who is out there monitoring open source LLM outputs, they actually saw that hallucination happen.
Oh, wow.
Yeah, and they immediately go to the Python package index, publish a malicious package under that exact hallucinated name, and then they just sit back and wait.
Because they know your pipeline is going to come looking for it.
Exactly. The second your automated pipeline runs its dependency resolution, it downloads the attacker's malware. I mean, it totally bypasses every firewall you have and just hijacks your entire MLOps infrastructure from the inside out.
It is honestly terrifying. And it completely rewrites the rules, you know?
Yeah.
The attack vector you're describing, it circumvents all our traditional perimeter security.
Right.
Because we aren't just defending against external breaches anymore. We are dealing with systems that proactively pull in their own destruction based on, well, probabilistic text generation.
Yeah, the tools building the software are basically fabricating the attack surfaces at the exact same time.
Exactly, which fundamentally changes the entire threat landscape.
Which is exactly why we are doing this deep dive today. Our mission for you, the listener, is to chart a chronological roadmap for securing machine learning workflows from the ground up.
It's so needed right now.
It really is.
Mm-hmm.
We are moving past the theoretical stuff. We want to get into the absolute gritty mechanics of how you actually secure these completely opaque, constantly shifting systems.
Yeah, we're talking the mathematics of data poisoning, the cryptographic sealing of deployment pipelines, the whole 9 yards.
And even getting into the internal architecture of these crazy multi-agent AI systems that are out there autonomously discovering and patching zero-day vulnerabilities at basically machine speed.
Which is mind-blowing. But to even navigate a landscape this complex, we really need a rigorous operational model, a map.
Right. Can't just wing it.
No, definitely not. So we are going to anchor our entire discussion today in the Ericsson reference architecture.
Which is incredibly helpful.
It is, because instead of looking at machine learning operations as this chaotic web of scripts and random data dumps, this framework mathematically categorizes the entire life cycle.
9 sequential stages, right?
Yep. Exactly 9 stages, running from the very first architectural design phase all the way through continuous training and, live inference monitoring. It basically lets us systematically apply deterministic security controls to these highly probabilistic systems.
But before we start locking down that 9-stage architecture, I think we really need to acknowledge that managing this level of pipeline complexity, it requires dedicated, specialized infrastructure.
No, absolutely. It's not a DIY kind of thing.
Not at all. Which is why I want to quickly highlight our sponsor for this deep dive, CISOmarketplace.com. Because when you're dealing with these really sophisticated threats like hallucinated package squatting or even subtle mathematical data drift.
Which is a nightmare to catch, by the way.
Completely. Mm-hmm. You really need the kind of robust frameworks that they provide over at their CISOmarketplace.services program.
Right.
They have this highly specialized 6-pillar AI security department, and they also offer offensive AI services, which is perfect because those services are designed to actively stress test the exact types of machine learning pipelines we're going to dissect today.
And honestly, that offensive stress testing is critical, especially when you realize exactly why our traditional defensive paradigms are just, completely failing us right now.
Yeah, let's get into that. Because for the last decade, the gold standard has been DevSecOps, right? The whole idea of shifting security left.
Right. DevSecOps was the holy grail. But the problem is, it was engineered for deterministic code bases.
Meaning code where A always leads to B.
Exactly. It's built on the premise that if you analyze a source code, you can map the exact execution path of the application. But machine learning just shatters that entire premise.
Because of the opacity problem.
Yes, the problem of opacity.
I was actually looking at how traditional SAS tools, static application security testing tools, how they parse code.
Yeah.
And they basically rely on building an abstract syntax tree, right?
Yeah, and they map out the logic nodes like if this happens, then do that. Or here's a while loop.
But if you take a SAS tool and point it at a deep learning model, it's just, there's no logic tree.
None at all.
The logic is just entirely contained within this serialized file of, what, millions of floating point numbers.
Yeah, millions or billions of weights representing the tensor states of a neural network.
It's like using traditional AST on an ML model is basically like using a spell checker to grade an advanced calculus exam.
That is a perfect analogy.
Like, the spell checker might catch a misspelled comment in the margin of your Python script, but it has literally no mathematical capability to analyze the neural weights.
Yeah.
It can't tell you if the model's logic is sound or if someone hit a backdoor in there.
Right. The mathematical disconnect is total. A standard SAS tool, it's looking for hard-coded secrets or maybe SQL injection patterns.
Yeah.
It has absolutely no mechanism to evaluate whether a PyTorch script lacks proper tensor normalization or if the gradient descent algorithm itself is susceptible to, like, an adversarial perturbation.
Because the logic wasn't written by a human. It was inferred from the data during training.
Exactly. And that actually brings us to the second massive failure point of traditional DevSecOps, which is the mechanics of continuous training.
Oh, this part is wild.
Yeah.
Because in standard software, a release cycle is pretty static.
Very static. You compile version 1.0, you sign it, and those binary hashes stay completely identical until a human developer actively pushes version 1.1.
But in an automated MLOps pipeline, the model is constantly rewriting its own decision boundaries.
Constantly.
So if you have this pipeline pulling yesterday's live user data and it runs a new stochastic gradient descent epoch and then updates the model weights automatically every 24 hours, the system fundamental behavior is mutating daily.
Yeah, you are introducing these non-deterministic delta shifts into a live production environment, basically without human review.
Which is terrifying.
It is. This continuous retraining completely blurs the boundary between development and runtime operations. And tracking the provenance of those changes, it's just a mathematical nightmare.
Because of the non-determinism, right? Like, you can't even reproduce the exact same model twice.
Exactly. Due to massive dataset permutations, the use of random seeds when you initialize, and even just the floating point non-determinism inherent in GPU parallel processing, reproducing an exact ML model is functionally impossible.
That's so crazy to me. If you run the exact same data set through the exact same training loop twice, you get different weights.
Yes. The resulting neural weights will exhibit microscopic variances, so you cannot rely on traditional cryptographic hashing to verify model integrity across different training runs.
Wow. Okay, so if the models are basically opaque tensors and they are constantly shifting their own weights based on non-reproducible GPU calculations, how on earth does a governance team manage this from a security perspective? It seems impossible if you just focus on the artifact itself.
Well, you hit the nail on the head. You have to shift the governance model away from the code. You have to focus almost entirely on the human workflows and the pipeline choke points.
Got it.
That is the core tenet of modern MLSecOps. You enforce security by strictly defining the personas managing those Ericsson architecture stages we talked about.
Right, okay.
You assign specific deterministic validation gates to the AI or ML engineer, the data engineer, and the data scientist, and they navigate the OWASP machine learning top 10 security risks through those gates. You basically lock down the environment they work in rather than trying to statically analyze the probabilistic output they generate.
Okay, that makes a lot of sense.
Yeah.
So let's actually map those personas to the architecture starting right at the headwaters. Stages 1 and 2 of the Ericsson framework: planning, design, and data engineering.
Yes, the foundation.
Because if the data ingestion pipeline is compromised, the model is basically poisoned before a single tensor is optimized, right?
Exactly. So stage 1 requires shifting your threat modeling to actually accommodate adversarial machine learning. Governance teams have to use visual architectures like OWASP Threat Dragon.
Threat Dragon, okay.
Yeah, by explicitly drawing out the data flow boundaries and integrating the adversarial ML threat matrix, teams can mathematically identify exactly where the inference API is exposed.
Oh, so you can lock it down early.
Right. It allows them to implement rate limiting long before a single line of code is ever written, which mitigates OWASP ML05, which is model theft.
But the real structural defense really kicks in during stage 2, right? With the data engineer persona.
Yes.
Let's call her Dibby. So Dibby manages the large-scale ingestion and transformation pipelines, and her main adversary here is OWASP ML02. Data poisoning.
Right, and the mechanics of data poisoning are just fascinating because they don't actually require an attacker to breach a server or inject executable code.
That's the scary part.
The attacker just manipulates the statistical distribution of the training data.
It's like slowly adding microscopic lead weights to one side of a roulette wheel.
I love that analogy, yes.
The house doesn't even notice the wheel is being tampered with. But over millions of spins, the statistical outcome inevitably shifts entirely in the attacker's favor.
Exactly. So if Dibby is ingesting millions of telemetry logs for, say, an anomaly detection model, the attacker just drips these highly sophisticated anomalous logs into the feed, but intentionally labels them as benign.
Sneaky. So what does that actually do to the model?
Well, it forces the model's optimization algorithm to alter its decision boundary. During backpropagation, the model updates its weights to minimize the loss function against those corrupted labels. It effectively learns a blind spot.
Oh, wow. So the model will subsequently classify that specific type of malicious attack as perfectly normal traffic.
Yep. The attacker has backdoored the neural network using absolutely nothing but data.
Okay, so defending against that, it means Dibby has to analyze data distributions at a massive scale before it even hits the training loop. And she can't exactly manually inspect millions of logs.
No, definitely not.
I know a lot of data engineering teams rely heavily on API-level validation using frameworks like Great Expectations. And when you really dig into how Great Expectations functions, it's not just doing basic, null value checks.
Right, it's much deeper than that.
It calculates these really complex statistical metrics over massive data sets in parallel.
Exactly. It allows Dibby to define deterministic unit tests for basically probabilistic data. She can actually program the framework to calculate things like the Kullback-Leibler divergence or the Kolmogorov-Smirnov test across incoming data batches.
Wait, the Kullback-Leibler divergence, what does that actually measure in this context?
It essentially measures how one probability distribution differs from a reference distribution. So if the distribution of labels in Tuesday's data batch diverges statistically from the established baseline of, say, the last 6 months, the ingestion pipeline just halts instantly.
Oh, that's brilliant. It enforces strict mathematical boundaries on what the model is even allowed to learn from.
Exactly. But when a divergence is detected, you need a quick mechanism to actually excise that poisoned data. And this is where data version control, or DVC, becomes critical.
Right. And DVC doesn't operate like standard version control, right? It doesn't store the actual terabytes of data in a Git repository.
No, that would be impossible. It actually creates a Merkle tree of the data set. It hashes the massive data files, stores the actual blobs in an external S3 bucket, and then only tracks the cryptographic hashes in the Git repo.
Okay, so that underlying Merkle tree architecture is vital for lineage.
Yes.
Because if Dibby discovers that the ingestion stream was poisoned, say, 3 weeks ago, she can just use DVC to instantly check out the cryptographic hash of the dataset from 4 weeks ago.
Exactly. And then the pipeline immediately purges the local cache and pulls the exact uncorrupted data blocks from cloud storage. It restores the mathematical foundation of the training environment back to a known safe state.
Which sounds great, but I have a question here. Differentiating between a coordinated, slow-drip data poisoning attack and just natural statistical drift in real-world user behavior, that has to be arguably the most complex problem in ML governance.
Oh, it absolutely is, because the mathematical signatures look nearly identical in the short term.
Right. Identifying that really subtle adversarial intent requires correlating this statistical divergence with external threat intelligence feeds, which, frankly, is precisely why leveraging a specialized service like CISOmarketplace.com and their 6-pillar AI security department is basically a strategic necessity.
Yeah, you really need analysts who deeply understand the nuances of adversarial data manipulation.
Exactly. So once the data engineering foundation is cryptographically secured and statistically validated by Dibby, the pipeline flows into stages 3 and 4, experimentation and ML pipeline development.
Right.
And this is where the data scientist persona, let's call him Daniel, he takes control of that curated data to actually build and tune the algorithms.
Yep. And Daniel's main objective during the experimentation phase is to actually harden the model against inference time attacks, long before the pipeline is fully automated.
Inference time attacks, meaning attacks that happen when the model is already live.
Exactly. He is working to prevent evasion attacks. That's where an adversary crafts an input specifically designed to fool the deployed model. And the framework of choice here is usually the Adversarial Robustness Toolbox, or ART-T. And the internal mathematics of art are just incredible.
Yeah, because it doesn't just blindly guess how to trick the model, right?
Yeah.
It uses the model's own gradients against it.
Exactly. You were referring to techniques like the fast gradient sign method, or FGSM.
Right.
So RT programmatically accesses the model's loss function. Instead of updating the model's weights to minimize loss, which is what happens during normal training, ART calculates the gradient of the loss with respect to the input data.
Oh, okay.
It mathematically determines the exact minimum perturbation required to maximize the loss and force a misclassification. So it alters the input tensor, maybe changing a few pixel values in an image by totally imperceptible amounts, and feeds it back into the model to verify the evasion.
That is so wild.
Yeah.
So by systematically running FGSM and other mathematical attacks during the experimentation phase, Daniel basically generates a massive corpus of adversarial examples.
Yes.
And then he injects those adversarial examples back into the training data set with the correct labels.
Exactly. He is essentially forcing the model to study the exact mathematical perturbations that break it. It smooths out the decision boundaries, so those specific gradient-based attacks will just fail in production.
So adversarial training fundamentally increases the structural integrity of the resulting tensors.
Absolutely. But building a robust model is really only half the battle in this phase. Daniel then has to automate the training workflow in stage 4, which is ML pipeline development.
Oh, and this is where we return to the nightmare scenario we introduced at the very beginning of the deep dive, OWASP ML06, AI supply chain attacks, and the phenomenon of hallucinated dependencies.
Yes. The vulnerability lies in exactly how package managers resolve dependencies.
Right.
When Daniel runs an automated pipeline, tools like Python's pip look at the requirements.txt file. And if an AI assistant hallucinated secure ML tensor utils, pip doesn't verify the author. It simply queries the public Python package index.
And if an attacker has squatted on that exact string name, pip just downloads the tarball, extracts it, and routinely executes the setup.py file.
Yep. Instantly detonating the malware with the privileges of the pipeline runner.
It's just a devastating exploitation of the pipeline's basic trust in public registries.
It really is. So to combat this, Daniel must integrate deterministic supply chain auditing directly into the CI/CD runners.
Right.
He has to utilize tools to generate a software bill of materials, an SBOM.
Like Cyclone DX or SPDX?
Exactly. Frameworks like that parse the dependency trees, including transitive dependencies, which are, the packages that your packages rely on, and they map every single cryptographic hash and version number.
Got it. And then this SBOM is automatically cross-referenced against vulnerability databases and internal allow lists before the pipeline is even permitted to execute.
Correct. But auditing the static dependencies only stops the hallucinated packages. Daniel also really needs to validate the runtime stability of the ML APIs.
Which is tricky, right? Applying traditional fuzzing tools to machine learning endpoints introduces some pretty severe complications.
Huge complication.
Because if you point a standard fuzzer at a REST API, it blasts malformed packets and basically looks for a TCP timeout or segmentation fault. But machine learning models, they just fail silently.
Exactly.
If you throw garbage data at a tensor inference endpoint, it might not crash the server at all. It might just return a classification with a 0.001% confidence score. And the wrapper application might just blindly accept that, which leads to catastrophic downstream logic failures.
Right. That silent failure state necessitates specialized dynamic testing. Daniel has to adapt advanced fuzzing architectures like AFL++.
AFL++.
Yeah. Because AFL++ utilizes compiler-level instrumentation, it tracks code coverage at the branch level. Daniel writes a specialized Python harness that reps the ML API.
Okay.
And then the fuzzer mutates the input tensors, feeding in NaN values, infinite floats, or massively out-of-bounds integers. AFL++ tracks the execution path through the data preprocessing scripts and the tensor allocation libraries.
So if a specific malformed input causes the preprocessing script to consume excessive memory, or maybe bypasses a crucial normalization branch,
AFL++ detects that structural deviation, which allows Daniel to patch the API layer before it ever reaches deployment.
Okay, wow. So the data is validated by DIBI, the model's mathematics are hardened against FGSM by Daniel, and the automated pipeline is locked down with SBOMs and compiler-instrumented fuzzing. That perfectly transitions the lifecycle into phase 3, deployment, continuous training, and monitoring.
Yes.
And this is where the AML engineer persona, Allison, she takes over to orchestrate the live production environment.
Right. Allison manages stages 5 through 9. And she focuses heavily on stage 7, which is continuous training. The CT pipeline automates the ingestion of fresh production data to retrain the model and prevent it from becoming obsolete.
But this automation introduces OWASP ML model skewing.
Yes, exactly.
Which is that adversary-induced feedback loop drift we touched on earlier.
Right. If an attacker maps the telemetry gathering mechanisms of the CT pipeline, they can intentionally generate toxic data patterns right in the live environment.
And because the retraining trigger is fully automated, the pipeline eagerly ingests this toxic data, recalculates the neural weights, and just redeploys the degraded model.
Exactly. The attacker basically weaponizes the system's own automation to orchestrate a slow-motion denial of service.
So to prevent an attacker from manipulating the deployment state or swapping out the model artifacts during these automated updates, Allison really has to implement rigorous cryptographic enforcement.
Yes. And the industry standard mechanism for this is Sigstore.
Sigstore.
Sigstore completely revolutionizes artifact signing because it ties cryptographic signatures to ephemeral identities.
Right, and the internal architecture of Sigstore is brilliant, specifically because it eliminates the absolute nightmare of managing long-laid PGP keys.
Oh, managing PGP keys is the worst.
It really is.
Yeah.
So when Allison CT pipeline generates a newly trained model file, the pipeline requests an OpenID Connect, or OIDC, token from an identity provider.
Yeah.
Basically proving it is the authorized GitHub Actions runner.
Yep.
And then Sigstore Certificate Authority, Solcio, receives that token and issues a short-lived, ephemeral X.509 certificate. And it's tied strictly to that pipeline's identity for just a few minutes.
Exactly. The pipeline uses that ephemeral certificate to cryptographically sign the model's SHA-256 hash. But the crucial component here is the transparency log called RECOR.
RECOR, okay.
The signature and the public key are immediately published to RECOR, which is an immutable append-only ledger. Once the ephemeral certificate expires just minutes later, the cryptographic proof lives forever on the ledger.
It's like putting a unique unbreakable wax seal on a classified document.
Yeah.
If that seal is broken or swapped out between a secure training lab and the live customer server, the deployment freezes instantly.
Because when the deployment orchestrator attempts to pull the new model into the live serving environment, it first queries RECOR. If the mathematical signature of the model file doesn't perfectly match the entry on the immutable ledger, the orchestrator just kills the deployment. It provides mathematically verifiable model transparency.
That is so clean. That cryptographic seal guarantees the structural integrity of the artifact as it enters stage 8, model serving.
Yes.
But once the inference API is live on the public internet, the model is exposed to OWASP ML03, model inversion, and ML05, model theft. We mentioned rate limiting earlier, but the actual mechanics of model theft are just insidious.
Very.
Because an attacker doesn't need to breach the server, they just exploit the high-precision confidence scores returned by the API.
Right, so if a live API returns a classification along with an exact probability vector like, say, 98.7265% confidence it is Class A and 1.235% confidence it is Class B, an attacker can systematically query the API with millions of slightly varied inputs. And by mathematically analyzing how those high-precision confidence scores shift in response to the input variations, the attacker can basically estimate the model's decision gradients.
Wow.
And they use those gradients to optimize a surrogate model on their own local hardware.
Without ever touching the original model.
Exactly. Over time, the surrogate model converges, and they've effectively cloned the proprietary intellectual property of the enterprise model without ever touching the original weights.
That's crazy. So to combat that gradient estimation, Allison deploys the model via secure orchestration environments like Selden Core.
Yep.
And she configures the API gateways to aggressively truncate the confidence scores. So returning only a flat integer percentage rather than a high-precision float, which basically mathematically degrades the attacker's ability to calculate the gradients.
Right. It starves them of the mathematical detail they need. Furthermore, she wraps the endpoints with runtime security scanners. She implements LLM-specific vulnerability scanners like Girac or Protect AI's LLM Guard to enforce real-time input sanitization and output filtering.
Right.
They analyze the semantic structure of incoming queries to block prompt injection payloads before they even reach the tensor logic, which leads directly into stage 9, continuous monitoring.
Okay, the final switch.
Allison establishes observability pipelines using frameworks like Evidently or YLogs, and these frameworks calculate the statistical distribution of the live inference requests against the established baseline of the training data.
So back to statistics.
Yes. If the Jensen-Shannon distance between the live traffic and the baseline exceeds a programmed threshold, the system flags a potential adversarial data drift attack in real time.
I have to say, successfully architecting this level of cryptographic enforcement, gradient protection, and statistical monitoring across a live deployment, it requires specialized offensive validation. You have to ensure these controls actually hold up under fire.
Oh, absolutely. You can't just set it and forget it.
Exactly, which is exactly where the offensive AI services from our sponsor, CISO Marketplace.Service program, become completely indispensable because they will mathematically pressure test those Selden core deployments and the Sigstore transparency logs to ensure your MLOps architecture is actually airtight.
And you really need that validation because while we've meticulously mapped the defensive perimeter using the Ericsson architecture, we've locked down the data, the algorithms, and the deployment pipelines. Relying purely on a defensive architecture is basically a losing battle against automated threats.
Right, it's not enough anymore.
No. The paradigm is shifting toward proactive, autonomous remediation. We are entering the era of the Cyber Reasoning System, or CRS.
And the ultimate validation of this concept was the DARPA Artificial Intelligence Cyber Challenge, AIECC.
Yes, exactly.
DARPA basically demanded that teams engineer systems capable of autonomously discovering vulnerabilities in really complex C and Java code bases, mathematically proving the exploitability, and then generating highly accurate structural patches with zero human intervention.
Which sounds impossible.
But Team Atlanta won $4 million proving it could be done. But I want to talk about the runner-up, Trail of Bits, because they built a system called Buttercup that is just fascinating. It successfully patched vulnerabilities across 20 distinct common weakness enumeration categories with an astonishing 90% accuracy rate.
Yeah, the efficiency metrics of Buttercup completely dismantled the assumption that autonomous cyber reasoning requires, massive computational overhead. Trail of Bits spent roughly 181 per competition point, orchestrating over 100,000 large language model requests.
That is insanely cost-efficient.
Very. But the architecture of Buttercup is what's really vital to understand, because it achieves that 90% patching accuracy specifically because it does not rely on an LLM to just blindly read source code and guess where the vulnerabilities are.
Right, because if you just paste a massive C++ file into an LLM and ask for a security review, it will just hallucinate buffer overflows on lines that don't even exist, just like it hallucinated those Python packages.
Exactly. Buttercup overcomes this by deploying a strict multi-agent architecture. It physically separates the generative creativity of the LLM from the deterministic mathematical proof required for software patching.
It executes a really highly orchestrated step-by-step pipeline. Step 1 is test case generation, right?
Yes.
The system utilizes prompting strategies to instruct the LLM to act purely as a threat actor, brainstorming edge cases. The LLM reviews the target application's API contracts and generates thousands of highly complex, malformed inputs designed specifically to break the parsing logic.
And then in step 2, those generative test cases are stripped away from the LLM and fed directly into classical deterministic fuzzing engines, specifically libfuzzer and jazzer.
Okay, libfuzzer. How does that fit in?
So libfuzzer operates as an in-process fuzzer. It is linked directly with the target binary. It executes the LLM's malformed inputs at blistering speeds, tracking the CPU execution paths via compiler instrumentation.
Got it.
When an input triggers a memory violation, libfuzzer generates a concrete crash dump. The fuzzer provides the deterministic mathematical proof that a vulnerability genuinely exists, which completely eliminates the possibility of an LLM hallucination.
That's a perfect synergy. So while the fuzzer isolates the crash state dynamically, step 3 engages static analysis to map the architecture. The system deploys a deterministic parsing tool called tree sitter.
Yes, tree sitter is fantastic.
Unlike traditional static analysis tools that rely on, fragile regular expressions, tree sitter generates a highly precise, concrete syntax tree of the entire code base in milliseconds.
Right.
It provides an exact structural map of the data flows, variable assignments, and function call graphs leading up to the exact line of code that libfuzzer proved was vulnerable.
And that brings us to step 4, which is where the orchestration magic actually happens: contextual understanding and patch generation.
Okay.
A specialized LLM agent is provided with the concrete crash dump from the fuzzer and the exact mathematical syntax tree from TreeSetter.
Oh, so it's fully grounded.
Exactly. The AI is no longer guessing. It is constrained by absolute structural reality. It understands precisely how the memory corrupted and where the logic failed in the syntax graph. Only then does it generate the specific lines of C code required to patch the flaw.
And then it tests again.
Yes, that patch is automatically recompiled and retested by libfuzzer to ensure the memory violation is actually resolved and no regressions were introduced. That multi-layer deterministic constraint is exactly how Buttercup achieves autonomous patches exceeding 300 lines of code.
That is just incredible. But the orchestration of these highly disparate tools, an LLM generating tests, an instrumented C++ fuzzer executing them, a syntax parser mapping the tree, and another LLM writing the patch that requires an advanced communication protocol. You can't just have human engineers copying and pasting terminal outputs between these systems.
No, of course not. The architectural breakthrough enabling this seamless autonomy is Anthropic's Model Context Protocol, or MCP.
I was reviewing the JSON RPC 2.0 payload structures that power MCP, and the elegance really lies in its strict standardization. MCP establishes a universal client-server architecture for AI agents.
Right.
The AI application acts as the MCP client, sending a standardized initialized request to the MCP server, which exposes the underlying enterprise security tools. When the AI needs to map the codebase, it sends a tool-call JSON payload specifying the TreeSetter parameters.
Exactly.
The MCP server executes the deterministic parking tool and returns the concrete syntax tree back to the AI's context window as a structured JSON response.
So by standardizing the transport layer, MCP allows the AI agent to orchestrate parallel execution across multiple security tools simultaneously, based entirely on natural language reasoning.
Right.
It's the connective tissue that transforms a standalone chatbot into an autonomous, agentic cyber reasoning system capable of navigating enterprise environments at machine speed.
But the reality is, most engineering teams do not have a bespoke, multi-agent MCP architecture orchestrating instrumented fuzzers.
Oh, no, definitely not.
They have a junior developer pasting proprietary pipeline scripts into a standalone web-based LLM interface and asking it to find vulnerabilities. And when you attempt to use a standalone generative model as a SaaS tool, the result is an absolute operational disaster that the industry has affectionately dubbed AI slop.
Yes, AI slop. It's a huge problem. And the slop is a direct consequence of substituting token prediction for deterministic analysis. Let's compare a standalone LLM to a highly trusted open-source Python SaaS tool called Bandit.
Okay, Bandit.
Bandit operates by parsing the Python code into an abstract syntax tree. It then deploys specific visitor nodes that traverse the tree, looking for exact, mathematically defined risk patterns.
Like what?
Like the instantiation of the exec function, or maybe the presence of hard-coded cryptographic keys based on Shannon entropy calculations.
Right, and because Bandit relies on strict AST traversal and the IMIRI Common Vulnerabilities and Exposures Dictionary, its false positive rate is totally predictable and manageable.
Yeah.
If it flags a vulnerability, it points to the exact line number in the syntax tree.
Exactly.
And critically, Bandit assesses its own limitations. It outputs structured confidence scores. If the entropy calculation on a string is borderline, Bandit explicitly reports low confidence, which allows the human developer to quickly triage the alert.
A standalone LLM lacks both the syntax tree and the CVE definitions. It is literally just a probabilistic text engine predicting the next most likely token based on its training data.
Right.
Because it has ingested millions of security reports detailing SQL injections in database utils files, if you ask it to review a generic web application, the mathematical probability of it generating a string about a SQL injection in a database utils file is extremely high.
Regardless of whether that file actually exists in your repository.
Yes.
So it hallucinates the vulnerability, it hallucinates the file path, and it hallucinates the line number.
Yeah.
And because of the nature of the generative model, it presents this absolute fiction with highly articulate linguistic confidence.
Exactly.
Relying purely on a generative AI for security scanning is basically like hiring a brilliant but compulsive liar as your night watchman.
That's a great way to put it.
They might occasionally spot a master thief that a camera missed, but they'll also tell you dragons are in the vault. You must pair them with the traditional security camera, the deterministic tool, to filter out the fiction. Because if it outputs a beautifully formatted markdown table detailing a critical 0 day that requires immediate attention,
It forces the human analyst to waste hours manually traversing their file system hunting for a ghost. And then developer trust in the security tooling completely collapses.
So rebuilding that trust requires implementing sophisticated hybrid triage strategies within the Security Operations Center. You have to deploy architectural layers to filter the AI slop before it ever reaches a human analyst.
Right.
The first strategy is deploying secondary LLMs constrained by strict validation scripts. When the primary, noisy AI scanner generates an alert, a lightweight script triggers a secondary LLM.
Like Claude, for instance.
Yeah. The script forces the secondary AI to specifically cross-reference the hallucinated alert against the deterministic output of a tool like Bandit. If the secondary AI cannot mathematically correlate the reported vulnerability with the deterministic syntax tree, the alert is instantly purged from the queue.
That's a great filter. Organizations are also turning to deep learning classifiers to silence the noise. Security researchers are training convolutional neural networks, or CNNs, to recognize the structural patterns of an LLM hallucination.
How does a CNN do that?
The CNN vectorizes the scanner's output text and the target codebase, mapping them into high-dimensional space. Because hallucinations often exhibit specific semantic structures and lack tight coupling to the underlying code topology, the CNN learns to classify the alert as slop with really high precision.
Wow.
Deploying these CNN classifiers ahead of the analyst queue has actually been shown to reduce false positives by over 20%.
And the most advanced organizations are synthesizing these strategies into specialized AI SOC analysts. Using lightweight, task-specific frameworks designed specifically for vulnerability validation, they program autonomous agents to conduct preliminary investigations.
Right.
When an alert fires, the AI SOC analyst automatically pulls the commit history, queries the SIEM for related execution logs, and attempts a basic non-destructive validation check. It separates the mathematically verifiable signals from the generative noise, which cuts investigation response times from hours down to literally minutes and drives false positive reduction rates as high as 90%.
It's a massive efficiency gain. But even when you stack the CNN classifiers and the AI SOC analysts to filter out 90% of the slop, the architectural mandate remains. The human analyst must serve as the final decision time override.
Absolutely.
Because even a multi-agent system executing an MCP workflow can misunderstand the complex business logic or the architectural intent of a highly specialized pipeline. It might flag a local environment file as a leak when it's actually just a local dev test.
Right.
The deterministic tools prove the math, the generative AI provides the context, but the human must validate the logic before a structural patch is actually committed to production.
So to pull all of these threads together, we have dismantled the illusion that DevSecOps can secure opaque tensor mathematics. We navigate the Ericsson architecture, establishing exactly how DIBI enforces statistical boundaries to prevent data poisoning.
And how Daniel utilizes RRT and fuzzing to mathematically harden the models against adversarial gradients and those hallucinated dependencies.
Right. We explored Allison's cryptographic lockdown of the continuous training pipelines, leveraging Sigstore's ephemeral certificates and Recor's immutable ledger to ensure model transparency, while also deploying inference endpoints designed to mathematically frustrate gradient extraction attacks.
We then analyzed the incredible mechanics of the Buttercup system, dissecting how Anthropic's MCP orchestrates the interplay between LLM creativity, TreeSitter's deterministic syntax parsing, and libfuzzer's compiler instrumented execution paths to autonomously generate 300-line structural patches.
And we concluded by confronting the operational reality of AI slop, mapping out the CNN classifiers and hybrid triage layers required to maintain operational trust. Executing a defense-in-depth strategy across this entire mathematical landscape is, frankly, an extraordinary undertaking.
It is a massive heavy lift for any team.
It really is, which is why I want to emphasize once more that organizations do not have to engineer these complex defensive frameworks in isolation. Our sponsor, CISOmarketplace.com, provides the exact expertise required to navigate these threats.
They are phenomenal at this.
Whether you need to audit your pipelines for hallucinated packages, or you need to deploy offensive AI services to pressure test your Selden core deployments against model theft, I highly recommend exploring their CISOmarketplace.service program to engage their specialized 6-pillar AI security department. It really is the strategic advantage you need to secure your infrastructure.
You know, when you step back and look at the velocity of the systems we have discussed today, it leaves us with an incredibly daunting operational reality. We have detailed how AI SOC analysts are filtering thousands of alerts in minutes, and how systems like Buttercup are autonomously compiling, fuzzing, and deploying complex structural patches at machine speed.
Yeah.
But throughout this entire roadmap, we have maintained that the human must be the final decision time override.
The ultimate backstop against the machine, basically.
Exactly, but consider the actual trajectory of the threat landscape. As these defensive multi-agent architectures accelerate, they are actively engaging offensive AI systems that are dynamically mutating malware, generating hallucinated dependencies, and launching millions of sophisticated adversarial gradient attacks in fractions of a second.
Right.
We are transitioning into a state of continuous, autonomous AI to AI cyber warfare executing deep within the silicon.
It's an arms race.
It is. So, as the sheer volume, mathematical complexity, and microsecond execution speed of these autonomous engagements scale beyond human cognitive limits, we have to ask a terrifying question. At what precise moment does the required human override cease to be a functional security control and simply devolve into an illusion of authority?
Why?
At what point does the human analyst become nothing more than a rubber stamp blindly approving the actions of an AI system because the human brain is literally, mathematically incapable of comprehending the war being fought on its behalf?
We are basically building autonomous machines to defend our autonomous machines, and just hoping we can still read the telemetry. It is a profound engineering challenge to leave you with. Thanks for joining us on this deep dive. We will catch you on the next one.